Hello, I'm Subula Hachiji, Assistant Professor, Department of Mathematics, GFGC and Government. As an assignment, I have prepared this video on mathematical modeling and its applications for refresher course on Linux and get organized by GFGC Harihara in coordination with IIT Mumbai. In this video, I am covering the topics mathematical modeling introduction, differential equations overview, differential equations approach in mathematical modeling, and some of the applications of mathematical modeling. First of all, let us know what is mathematical modeling. Mathematical modeling is nothing but a miniature representation of a real world problem. Here we visualize something that cannot be directly observed. A system of postulates, data, and interferences are presented as mathematical description of an entity or a state of affairs. See, mathematical modeling is nothing but a representation of a real-world problem in mathematical form with some simplified assumptions which helps to understand in fundamental and quantitative way and then solve. It is complement to theory and experiments and often to integrate them. Then this is the example of mathematical modeling. See, a real world problem is simplified as a working model. Then working models are represented as mathematical model. In the mathematical model, a set of formula is used and the computational model has been translated by using the mathematical model, and computational model by taking several values of the variables. It simulates and gives the results and conclusions, and by those results and conclusions, we interpret the best solution for real world problem. So this is how the mathematical modeling works. Then why these mathematical models are necessary? What is the use of it? These mathematical models are important to perform the experiments and to solve real-world problems which may be risky and expensive or time-consuming. And this emerged as a powerful and indispensable tool for studying a variety of problems in scientific research and process development and manufacturing. And this improves the quality of work and reduces the change and rework. Okay, and why and what is the use again? It comes into your mind. So the uses are, it solves the real world problems, as I said, and it facilitates to handle the complicated problems and having wide spread of applications in all basic sciences and engineering and technology, even in medicine, and so, even in our day-to-day life, we use these models for climate modeling, that means weather forecasting, aerospace science, trafficking in the space, technology, manufacturing and design, even how these space debris are when disposed, economics, material research, drug design, population dynamics, war-related problems, especially it is used in medicine and biology. Okay. See, some of the examples I have taken here. See, this slide represents the weather forecasting of the future days. For example, today there is a rain, so tomorrow whether it will be not, or a day after tomorrow, how hot it will be, what is the temperature, whether it is sunny or whatever regarding these atmospheric issues can be calculated by using this mathematical models. Okay, so this is also possible by this. And another example, this is the modern numerical technique of wide range of PDE, partial differential equations, are useful in science and engineering application. So this diagram represents the gravitational force of the earth. See, by using this gravitational waves, we are having now lot of TV programs and even radio. All this broadcasting is possible by using these waves. Even satellites and even space technology and space research, everything is working based on this, and we prepare the models for this, and based on that is calculated. And in the mathematical modeling, there are two types, the empirical models and theoretical models. Empirical models, by using experiments and observations, we can find the results. And theoretical models, statistical, mathematical, and computational. So by having these frameworks, we can calculate the values, theoretical values of an event. Then let us go to the overview of the differential equations. To make these mathematical models, we use the differential equations of first order as well as the second order and also partial differential equations. These three types of the equations are used in the mathematical modeling. First, let me tell you about the differential equation. The differential equation is nothing but a equation consisting derivatives of a function with respect to one or more variables. If it is with respect to one variable, then that is called as ordinary differential equation. This is represented as ODE. For example, d square y by dx square plus 2x dy by dx plus y is equal to sin x. This is an example for ordinary differential equation. Here, there is only one variable, derivative with respect to x, one variable we have. Okay, derivatives with respect to one variable. Then derivatives with respect to two or more variables is called partial differential equation. For example, I have taken one partial differential equation. Dou u by dou t is equal to dou square u by dou x square. I see in this equation t and x, two variables are there. Okay, that's why it is called as partial differential equation. Now, the order of the differential equation, that means the highest derivative of the equation is nothing but its order. See here, d square y by dx square plus 5 dy by dx whole cube minus 4y is equal to e power of x. Here, d square y by dx square is the highest, this one, power order of the this given equation. So, we have order is 2. Then coming to the degree of these equations, the degree of differential equation is highest exponent of the highest derivative in the equation. It is free from radicals. For example, in this equation, highest this one derivative is d square y by dx square and its exponential. That is, its power is 2. Therefore, degree of this equation is also 2. Degree of this equation is 2. But here dy by dx is the least derivative, but the highest derivative is d square y by dx square. Therefore, the degree of this is also equal to 2. Now, the difference between order of differential equation and degree of differential equation is here the highest derivative is order, and here the exponent of the highest derivative is called its degree. Then let's see how these differential equations are classified based on degree. Based on degree, we have two types, the linear differential equations, which a single equation is there, and non-linear differential equations. Here, two types of, that is algebraic as well as trigonometric terms are involved. So, linear and non-linear, these are the two types of differential equations based on degree. Then, based on its conditions, we have initial value problems and boundary value problems. Based on its conditions, initial value problem is the initial condition is given. It means a differential equation is subjected to the condition at the initial point. Example, all equations involving time are these initial value problems. That is, dy by dt is equal to 0.85y, where y of 0 is equal to 19. That means it is initial condition. At x is equal to 0, y of 0 is equal to 19. So that's why this problem is called as initial value problem. Then coming to the next type, that is the boundary value problem. It's nothing but a differential equation is subjected to the condition at initial and other end point. Both are considered. See, for example, we have taken an equation here, that is d square y by dx square plus y is equal to 0, and they have given two conditions. Y of 0 is equal to 0 and y of pi by 2 is equal to 3. Initially, when x is equal to 0, y value is also 0. This is initial condition. Then boundary, there is n condition is y of 5 by 2 is equal to 5 by 2. When x value is 5 by 2, y value is 2. This is the boundary condition. That's why we call these equations as boundary value problems. Then, how we can find the solution for differential equations? The solution can be found in two ways. That is the analytical method, and we have the other method called numerical method. Analytical and numerical methods are two types of methods. Then what is the solution of the differential equation? The solution of the differential equation is nothing but an expression which satisfies the differential equation is called the solution. For example, y is equal to sin x. If you substitute in this equation, that value will be equal to 0. Y is equal to sin x value will be equal. Just I'll tell you how it is. Y value is sin x. D square y by dx square means derivative of sin x is cos x. Then again, second order derivative, the derivative of cos x is minus sin x. So this equation reduces to minus sin x plus sin x. So it is equal to 0. That's why y is equal to sin x is satisfying this equation. Therefore, y is equal to sin x is the solution of this equation. Okay. And as I said, there are two methods, analytical and numerical methods. Now, let me take some examples of mathematical models. See, these are the differential equations. We call them as mathematical models because mathematical models are nothing but a set of formula. D square s by dt square is equal to minus g. It is an equation representing freely falling body. Since it is a freely falling body, the acceleration due to gravity is negative. That is minus g. And similarly, we have harmonic oscillator equation, Newton's law of cooling, then population growth, dp by dt is equal to kp. I'll discuss these things in the next slide. And the spread of diseases, that is dx by dt is equal to kxy. We have different various mathematical models. Let me take up the differential equations of first order where we use them. Okay, differential equations of first order are used in population growth models. See, the population growth can be estimated and even you can predict what will be the population of our country after 10 years. What was it behind 10 years like this. So we have two models, Malthus population model and the next model is Verhelst population model. First, let me discuss about the Malthus population model. Malthus population model, this is the graph of that one. The Malthus population model equation is like this. The statement is nothing but the rate of change of population is proportional to the population at present. At present, what is the population? So the rate of change of population in future will be based on that. Okay, it's proportional to that. Let me treat n is equal to population and dn by dt is proportional to n of t, where n of 0 is equal to n naught. dn by dt means it is a rate of change of population because n is population. When it is varying along with the time, that is dn by dt proportional to n of t and initially it is 0. That proportionality symbol is taken out and equated to kn of t. See, by using this equation, we calculate the population growth by using the final equation n of t is equal to n naught e power of kt. See, by taking this n of t is equal to n naught e power of kt, we can work out the population of USA at 1790 and 1800. That is in 10 years duration. This was the difference. So how it is varying, that can be calculated by using our mathematical model. And these results are graphically represented like this. Okay, but this Malthus calculation was failed because it was not having the preventive checks like fertility rate and postponement of the marriage cost of food, all these things, it was not having that preventive checks. But even though it has a feminine disease, war, and all these positive checks, so it has more sub-models, and that's why this model has been failed. So after that, the Dutch biologist Verhelst proposed the various constraints due to the finite resources, and he has given the beautiful mathematical model which is having many constraints. So that is dn by dt is equal to k into 1 minus n of t by n naught into n of t. Okay, so by using this model, we can calculate, that is dp by dt is equal to k into p into 1 minus p by m. So he has taken some population measures, and by giving different values for these constants and these variables, so we get the results like this. See, the USA population in 1820 9.6, 1830 12.9 in billions, and 1840 17.1. But see the calculation of these models. Malthus model, it is 9.79, 13.3, and here is 9.7. See the accuracy of these two, 13.3, 13. See, Wilhardt's model, almost nearest to these values. USA population is 12.9 in 1830, but by the Malthus model 13.3 and Wilhardt's model 13. See, this is the nearest value, and this is exactly accurate. Okay, see, and all these things can be plotted in the graph also like this. Then the population growth model, it is also having various uses to calculate the growth of bacteria, growth of creatures, animals, and birds, and also in the birds, etc. Now let us go to the another mathematical model, the spread of diseases. Example, how the flu virus, Ebola, cancer, heart disease, now the COVID-19, how it spreads. See, when we have physical contact with the people like this, then our different day-to-day activities, and having lunch together, and sharing food, all these things are the possible ways of spreading the disease. Okay, see how you can calculate the duration of the spreading of the COVID or other diseases by using our models. Let us see. The spread of diseases model, the statement of this is, rate at which the disease spread is proportional to the number of interactions between the number of people with the virus and number of people with the people, those who are not yet green, those who are not COVID positive. It means it is the interaction between the COVID positive people and negative people. Okay, so for this we have made a model, that is, we have taken two variables, t and x of t and y of t. X of t is people with the virus positive, y of t is negative. Okay, so dx by dt, it is the spreading of the disease, is proportional to x of t into y of t. Means how many interactions has been done with these two people. One is positive, another one with the negative. So by using this model, we can have the equation. So that equation is dx by dt is equal to ax of t into y of t. See, k is here, it is the proportionality constant, and by calculating this, we can find how long the COVID-19 will take to reach, to spread among the people, and also how it can be prevented, what precautionary measures can be taken, can also be calculated. Now, I have taken another slide for an example, how we can find the radioactive half-life using our mathematical models. See here, the mathematical model is dn by dt is equal to minus kn, and there is a negative sign because radioactive half-life is life, it is nothing but the decay of radioactive element of 1 gram into half gram. How many years it will take, that will be calculated by this. So the rate of change of 1 gram of radioactive element into half gram is calculated by using this one. Next, it is a random process, that is dn by dt is equal to minus kn, and the rate of decay is always depending upon the number of molecules of the radioactive element. If it is 1 gram and certain period, it becomes half. If it is 2 grams, certain period, it becomes 1. Like that, it reduces into half. It is negative because the number is decreasing, and k is the constant of proportionality. So, like this, even our differential equation of first order can be used to find the radioactive half-life of the radioactive elements. And another example is the mass spring system. The second order differential equations are used in this one. Even this mass spring system is used in all vehicles, that is shock absorbers, we say. So like this, the mathematical models are very, very useful in our day-to-day life. So right from our satellites to our, even to our day-to-day health, and even in the sports, and even in automobiles, biology, and even in weather forecasting, all these things